7. Again, we illustrate this one, so that means we illustrate this system. Okay. So now we eventually I want to have I want to build up a certain graph. It's like this. This is the time, and this is the output response. And compared to our command, so this is the unit ramp input. And what I want to show is the overlap of the CT to here. So something like this one. I don't know. I want to have the figure like this. Okay. So basically right now we're doing is the unit ramp input response. And everyone knows in Matlab, Matlab doesn't have such unit ramp command. So always we are using down the road is going to use the step input. Okay, we still use the step input for this purpose. So we keep this in mind, then we see how we prepare. The step input is based upon the closed loop function of C over R. Okay. So let me say the closed loop functions C over R equal to the numerator's closed loop and denominator of closed loop. Okay, whatever the content you can calculate by hand, or you can calculate. I'm going to show you by Matlab. Okay, whatever this is. And then when we do the unit step input response, is we put into this. So this is a really unit step input. Right now we're going to use this command, step command, to simulate this one. What we can do, we're doing is this. See as, if you remember, let me call this is the given name. Given name, whatever, GC, no. Name it. Okay, let me name it. Y. Okay, so let me define this as Y. So basically, we want to calculate this. The output is this input multiplied with output, right? And for unit step input, the R equal to 1 over S. So that is the one we take up in the step input. For the unit ramp input, we S equal the unit ramp is 1 over S squared, right? If we want to still utilize the step input command, then you need to revise your system in the way is this. This one you simply is 1 over S. You take this template for unit step input, then you move this another one as into here. Simply is you trying to virtually absorb one as from the numerator into here. So this will be your revised description of the system to simulate the unit ramp input by using the unit step input command. Okay? Okay, so that is one, keep that in mind. So here, here I'm kind of working the upside, the step back forward. So here we will have the denominators for the closed loop system, and we will have the numerator for the closed loop system. Okay, so something like this. Okay, so that is this one. And for the step input, what I will try is to using the numerators of the this system original, and then I'm going to work on this one. The S is absorbed into the denominator, which means multiply with additional S. Basically, it raises the power by 1. So here, U is this. D is denominator C, and then put 0 here. Can you see that? So basically this one, in terms of our description of the polynomial, simply we raise the power by 1. You know what I'm saying? Okay, good. So now that is our template, and then we can work on this. This is a closed loop system, and for our contents, in our textbook, I dig out we have such a command G1 and G2. If we have the feedback system like this, then the closed loop functions, the numerators C and D and C. So that's why you can use this command, numerator C, D and C equal to feedback, F-E-E-D-B-A-C-K. This is a particular command in Matlab, and then you put into numerators 1, denominator 1, numerator 2, and denominator 2 for individual systems. So I'm going to do it this one here. So right now for this case, the numerators is, so numerator 1 is the G1 equal to etc. etc. Okay. So basically for this system, you can see the G2 equal to 1 1. Okay, the G2 equal to 1 1 because that's a unit, and then G1 work on the G1. And furthermore, to work on the G1, we have another command. Let me use the color here. So say if we have a series combination, so say G1 here, G2 here. So this one, you can have the combined numerator denominators equal to, again, series, S-E-R-E-S, and then again, numerator 1, denominator 1, and numerator 2, and denominator 2, using this command. So in this way, I'm going to combine the two commands. I'm going to apply this first to get the expression for the series combinations. Okay, so that one is the numerators, denominators for this portion, series combinations, S-E-R-I-E-S. And then numerator 1 for this one, that is 1.77. And then denominator for this one, that is 1.5. And then for the second option, for the second system, numerator, that is 10. And then the denominator is 1, 1, 0. Okay? So basically, I sequentially describe the system, numerator, denominator in sequential, then I go to this one. Okay? So right now, I have an equivalent description of the combined. Then I come to here. I want to right now is work on the closed loop. For the closed loop, again, I pick up this one, and so here I have the numerator of the closed loop and denominator of the closed loop. That one using the feedback command. The feedback command, again, check into the syntax here. So numerator of this one, so that is what we found earlier. Okay, so that is the one for this one, and this one is from series. And now for this one, because here is our unitary feedback here, so that is 1, numerator is 1, and denominator is 1. I think that's it. Okay, so right now we don't need this because that one has been handled there. Okay, so that's it. And then here I want to confine my drawing. My plot is, for example, from 0 to 5 seconds. So here 0.1 until 5.1. This one meaning the increment of the calculations. Okay, the smaller, then you have more data points being plotted. The graph, then you basically the graph range. Okay, and so So to the end of this step, and that is to draw the C, this curve, the black curve here. Okay, so again, that is about the system response to the unit ramp, and which is being in the black curve here. I want to have an overlap of the command. So unit ramp. So here I hold on, and that means I'm going to overlap, and I'm going to plot, and basically the plot is this is the slope of one curved straight line. So basically I can just simply copy this one. The plot meaning to plot the x-axis and plot the y-axis. The y-axis. Okay, so that is the one here. So let me save it. Say lag controllers. Okay, LA. So we give it a try. So see what happens. Okay, something like this. You good? Here come to a bonus point. I made a mistake here. Actually, the information is a little bit insufficient because I forgot to put one more information. Anyone can find it. I will give you anyone or any people give you one bonus point to test 3. That is the huge one. Look at the system here. So right now we're dealing with the system, right? And any mistake. So right now I have applied the series combinations and to obtain the G1. And then I apply the feedback and to apply the whole things. I think I forgot one thing. 30 seconds. There's a bug here. You like this curve? You like this result? I don't like it because I know there's a mistake there. Garbage in, garbage out, that's always the most challenging bugs for engineers. The whole process is correct, perfect, no bugs, but there's something there. Right? 10 seconds.
Did you forget?
Okay, take one by one. No, go ahead, no hurry.
I think I was going to say should P and Z be positive, but
no, it's not.
Did you forget to put the KC value?
Oh, holy cow. Email, yes, email is your name.
Nice.
Okay? And the same thing, right? Okay. Here you can see I forgot to multiply the KC to here. Right? So let me modify this right here. So KC equal to our calculation is 0.0171 here. And then that KC must be going to here. Right? So this is our descriptions of this block. Okay? Okay, so we save it and then we produce the different figures and we compare. Okay, so we can run that again. So that looks like this. Okay, so the system looks like this. So so the system behaves like this, and so maybe here we see it's not so clear. So let me close it and figure another figure, and we can look at that one from the even bigger viewpoint, say 400. Okay, so one. I simply zoom out our viewpoint. So this is our system looks like. If we zoom out, we always have the steady state error. The steady state error is determined by So here I didn't calculate, but you should be able to calculate easily to determine the steady state error due to the unit ramp input. You can determine that one. And actually that one is equal to KV. And what is KV? The KV equal to, by definition, as equal to 0, S times G, C S times G. Okay, so you should be able to easily determine this one. When we have not zoomed out to see compared to this one that seems to have a huge discrepancies, right? And you might ask why, when after I correct this mistake, why the behavior become worse. I think here is due to our selections. Because here we have select our design route to be here. Once we design our design system, this one has determined the system performance. So such a worse performance basically is influenced by our selection at the very beginning. So if you don't like that performance, then you have to modify these locations. Again, when at the beginning I said that this one is calculated per certain design criteria, for example, damping ratio or frequencies, right? So if you don't like this result, then you have to modify your original design. Good. So that is the whole design kind of thinking. So let's stick with these options, and this is our option 1. So if you like, you can try the different scenarios. Say P equal to, I would say, the different scenario is, I would say, I have the second calculation. Let me quickly give that number to you. Okay. So the second one, I would say the P equal to I directly select my P is underneath that design. That is my second option for the design. Okay, and then under that situation, corresponding Z value will be equal to minus 0.377. Okay, and we see what happened. And again, corresponding to this value, then the KC, again, apply the magnitude criteria, KC will be equal to 0.0249. Will be okay? So again, this is the design option 2, and if we choose the P, we determine Z, this is the corresponding one. Simply that it has been repeated our process, and we can quickly see the result here. So let me set this back to 4. And this is 0.25 and 0.377, and then KC 0.249.
You're gonna have to change your series. Didn't reference P and Z.
Yeah, so that one should be minus D and minus D. Right, good, thank you. So now we see. Okay, so that is similar situation than before, right? So, but anyhow, so right now we have this program is running, then you should be able to allow to quickly change this scenario. But again, from the very beginning, the selection of the P is not arbitrary, right? Because that due to this phase angle criteria that has give a certain constraint. Okay, so that is pretty much is the whole thing. And to this point, the design of the controllers and the verification has been very rigorous already. Okay, so if you can fully handle this kind of thing, you should be ready to for the test. Okay, I think that's it, and that pretty much is everything. And if you have time to look to read our textbook provides a system is a third order system, a little bit more complicated. But the textbook provided a more comprehensive description. So, but the process is pretty similar to what we done here. Okay. That's it.